Hi Rockridge, this is Mrs. Berger, and today we are going to discuss graphing rational functions. Most classes split this into 2 days, part 1 and part 2, and had a little Desmos element to it. This video will cover day 1 and day 2 all in one, so you have one video to watch for graphing rational functions. So let's get right to it. Graphing rational functions, we'll talk about the standard form, the HK form, that we use for graphing rational functions. So that HK form looks like this. Y equals A over x minus h plus k. And if you remember, things that were h's in our other functions moved things left and right. Things that were k's moved things up and down. And things that were a's made things skinny or wide. And so that's the type of behavior that will be caused by h, k, and a in this as well. But things happen a little bit differently in rationals. The graph of the parent function y equals 1 over x. So h is 0 and k is 0 and a is 1. That graph looks like this. You have a point here and it comes up like this and it comes down like this, and then you have a point like this and it comes like this. So it's a two-part graph. Now, what happens between these two parts are these little boundary lines. These boundary lines are called asymptotes. We saw these with exponential functions and with logarithmic functions. But these asymptotes are these little invisible lines. They don't show up on your calculator, so you have to draw these in for me on your tests and quizzes. They don't show up on your calculator, but these little invisible lines that exist that basically say don't cross here. Okay, so this graph, the red graph, does not cross this vertical asymptote, nor does it cross this horizontal asymptote, these invisible boundary lines. These are shown as dotted or dashed lines on your graph, and you will be required to draw these in on your tests and quizzes so that you can show me where these graphs are not going to ever cross or not going to ever reach. Let's talk a minute about the points and why the algebra here causes the graph here. Let's think for a second about inputs and outputs into this function. If you were to input, let's say we input a 1 for x. If you were to replace x with 1, you would have 1 over 1, which is 1. So that's why the 1, 1 point exists on this graph. And if you were to input 2 into this graph for x, your output would be y equals 1 over 2, or 1/2. Which is why if you were to input 2 for x, this line should actually be down here a little bit. I didn't draw it very well. But it should get closer and closer, and you can imagine if you were to put 3 in, you would get 1 over 3 out. So 1, 2, 3, you'd have something way down here. So this graph actually looks more like this. It gets closer and closer. It gets to be a smaller and smaller and smaller fraction here. Okay? What would happen if you put -1 in here? What would happen if you input -1 into here? If you input -1 in for x, you would have 1 over -1, which is -1. So that's why -1, -1 exists on this graph. Similarly, if you were to input -2 into here, it would be 1 over -2, or -1/2. So that's why -1, 2 has an output of -1/2. Okay? So that's how that algebra causes this graph. Okay? Remember horizontal asymptotes. Whenever I ask you to write down or document your horizontal asymptote, you don't just tell me 0. You tell me the line y equals 0, or y equals k. Y equals 0 for this one, but y equals k is your horizontal asymptote. Always tell me y equals. Your horizontal asymptotes are lines. They are not just single values. Similarly, for your vertical asymptotes, these up and down, for our graph here, it's x equals 0, but the general form you need to tell me is x equal h. Okay, it's a line, the equation of the line, x equal h. So let's see this play out on something other than the parent graph. Let's do some shifting of these graphs. So let's take a look here. Y equals 2, so now A is 2, over x minus 3 plus 1. So now we have a shifting. And the thing that shifted here, or the things that shifted here, are not necessarily, you remember with the parabola, you had something like this, and when you shifted h and k, it was this center point that shifted left and right. Well, this time we're shifting the asymptotes left and right and up and down, okay? So this time we're going to take, instead of x equal 0 as our vertical asymptote, x equal 3 is our vertical asymptote for this one. Remember, x equals h is our horizontal asymptote. And remember, with the h's, we always flip the sign, right? So x equal 3 is our vertical asymptote. That was what this caused, this shift to the right of 3. Similarly, right here, a shift up 1 was caused by that k right there. A shift up 1, or y equals positive 1, is the equation of the horizontal asymptote. Remember, these are equations of lines. And then this 2, if you were to graph this on your calculator, this 2 would cause a little bit of a stretching out. It would cause a little bit of a stretching out. So you actually have, let's see, if you go like this and like this, you got a little bit of a stretch here caused by that 2. Okay? And the way you can figure these things out is by doing a table of values, or you could graph it on your graphing calculator, right? So let's see. I'm saying that this right here is a point, because if you were to input 1, 2, 3, 4 for x, if you were to input 4 for x, you would have 2 divided by 4 minus 3, that's 1. So you'd have 2 plus 1, so you'd have 3. So the point 1, 2, 3, 4, comma 1, 2, 3 is on this graph. And so on and so forth. Similarly, you have a graph that crosses here and here. Again, you can find this out with a table of values, or you can put this in your calculator. That's the two-part graph for this particular algebra up here. Now, y-intercept. Let's talk about how we find y-intercepts. How do you think you find this point right there? Well, what would you input to find this? You would input 0 for x to find the y-intercept. So if you were to put 0 in for x, you would have 2 over 0 minus 3 plus 1, which is the same thing as negative 2/3 plus 1. How many thirds is 1? It's 3/3. So negative 2/3 plus 3/3, that's positive 1/3. So that's why 0, 1/3, 0, 1/3 is our y-intercept. So we'll document that. 0, 1/3. Remember, always give me an x, y for my y-intercepts. That's what the y-intercept is for this particular graph. Now, there's a couple of different ways to document domain and range. Let me do set notation here for you. So domain, remember domain is what? Is that x values or y values? Hopefully you said x values for domain. So for domain, we have, let's see, this graph goes on and on and on and on forever this way. So this arrow indicates that we have existing graph all the way to here, and then it takes a break, right? It takes a break at this blue dashed line, this asymptote here. So it doesn't exist here. It exists, doesn't exist. And then on the other side of this line, it picks up again, and exists and exists and exists and exists for all other x values. So the domain of this two-part graph lives everywhere except that one place, right? The domain of this graph is x such that x does not equal 3. It equals everything else except 3. Okay? So that's the set notation way to do that. And then range, if if you go from the bottom to the top, this graph, this little arrow indicates that it's going to go down forever. So it exists, takes a break at the asymptote, and then picks back up on the other side of this asymptote and exists forever all the way up to positive infinity. So similarly, the range is y such that y does not equal 1. It equals everything else except 1. It lives everywhere else. It has a y value. It exists at every y value except the value of 1. So that's how we write those in set notation. So let's look at this other example here. Let's talk about the HK shifts here. So we've got this shift here of an asymptote going to the left 2. So we go left 2 for the vertical asymptote. So we draw it in, and we document the vertical asymptote as x equal negative 2. So VA is vertical asymptote, the up and down line, the no-go line. And then the horizontal asymptote is indicated here, down 4. 1, 2, 3, 4. So I must have a no-go line down here at negative 4, or y equals negative 4. Always give me these equations of these lines. Alright, so this graph is interesting. If you were to put it in your calculator, you would notice that this little negative 3 here would cause a stretching as well as a flipping of the quote-unquote quadrants. So if you've noticed so far, the parent graph and this example has a graph existing here and here. If you were to show number 2, you would see a graph in this quadrant here. Let's see if I can get this here drawn in here. And here, I believe. So you'd have a graph in this quadrant as well as this quadrant here. Okay, so that's what that negative 3 did. It stretched it wider, and it flipped from these quadrants to these quadrants, pseudo-quadrants. Now, again, how do we find, and we could have found those values that I just drew in there by doing a table of x and y. We could have done a graph on our graphing calculator and asked it to tell us a table of values, whatever you need to do to make sure that you've got this graphed in the right places. So now y-intercept, again, that's when I set x equal to 0. When I set x equal to 0 in this problem, I've got negative 3 over 0 plus 2 minus 4. So that is negative 3 halves minus 4. Now let's talk about how many halves 4 is. That's the same thing as negative 8 halves, right? Negative 8 halves is the same thing as 4. So that means I have negative 11 halves as my y-intercept. So what is that? That's about negative 5.5. So down 1, 2, 3, 4, 5.5 is my y-intercept. So I write that as 0, comma, negative, you can say negative 11 halves or negative 5.5. Okay. Now that y-intercept is helpful for sort of centering our graph here, or having a nice little, not centering, but having a nice little point, a reference point here to graph this. But it does not talk about our domain. Okay, so please don't make that mistake that a lot of students make. Your y-intercept is helpful for graphing, but not necessarily for stating our domain. Okay, our domain is where does this thing exist? This thing exists everywhere you see purple, right? Everywhere you see purple and beyond because of these arrows. Okay, so the domain is every x value all along here and every x value all along here. So don't make it stop at this y-intercept. Make it stop at the asymptote. Okay, so that means this graph lives from negative infinity. We're reading left to right. It lives, and then takes a break at this asymptote and then lives again on the other side. So our domain for this, and I'm going to write this the long way this time. The domain for this is from negative infinity to negative 2. We take a break at negative 2 and we go off to positive infinity. Okay, so that's what that break at negative 2 means. You need to pause the video and stare at that and make sure you understand why this is the other way to do the set notation. So interval notation versus set notation. They mean the same thing, we just make sure we take our break at -2. Our range, I'll do that in interval notation as well, just to show you that example. Our range for this is bottom to top y values. Live, live, live. Everywhere the purple. Live, 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 live. Don't stop here. It keeps living. It only takes a break at the asymptote. It only takes a break at the asymptote. And that asymptote we said was at -4. So our range is -infinity to the -4. Unify on the other side, we pick back up -4 off to infinity. So it lives forever there. Okay? So that was graphing part 1. There's definitely some extra practice that you can do on your own, but that's the general sense of doing graphing with HK format. Okay? We're not always going to have HK format, but that was graphing using the HK. When you see a rational function in this form, a over x minus h plus k, you can use those h's and k's and a's to graph your rational function and to document your horizontal asymptote, your vertical asymptote, and your domain and range. Now let's talk about graphing part 2. We need to talk a little bit about something called discontinuity before we get too much further. And discontinuity, we've been dancing around this topic with asymptotes already, so let's just document this for posterity here. Discontinuity is where the graph starts and stops. It's where the graph starts and stops. And it could start over again, right? And so we saw that happen with our vertical and horizontal asymptotes, right? Continuity is when we can draw something continuously without picking up our pencil, right? And we were drawing these things and drawing these things, and then we had to pick up our pencil to finish the graph, right? So discontinuity happened when we had to pick up our pencil on the other side of those asymptotes. There are 2 types of discontinuity. There is removable discontinuity, and that presents itself as a hole. And there is, shocker, non-removable discontinuity, and that presents itself as a vertical asymptote. Okay? So we could possibly show that with a graph that looks like this. You could have a graph that has a vertical asymptote here and a horizontal asymptote here, right? And then that graph looks like this. It could possibly look like this. Oops, I didn't mean to do that. There we go. Looks like this, and then maybe it stops and there's a hole in it and picks back up again, and then maybe it picks back up again on the other side like this. Okay, so we saw 2 different types of discontinuity. We saw a removable piece of discontinuity, this hole right here, and we saw non-removable discontinuity, this vertical asymptote right here. Okay, so those are the 2 different types of discontinuity. You'll need to understand those. And we're going to see how that plays out here. So for purposes of our discussion, when you see a rational function, you're not always going to see it in HK form. You might see it with just one type of function on top and one type of function on the bottom, or what we call P of x and Q of x. So a rational function with P of x on top and Q of x on the bottom has a couple of different properties to it. So I'm going to switch back and forth between the P of x and Q of x terminology and the top and bottom terminology. So if I'm talking P of x, I'm talking top. If I'm talking Q of x, I'm talking bottom. And we'll see how that plays out here. So we have a little bit of a decision tree on a lot of this stuff. Again, a hole in the graph that's removable discontinuity. It presents itself as a hole here, removable discontinuity. And that occurs when P of x, or the top, the numerator, and the denominator, or the bottom denominator, or Q of x. P of x is the numerator, Q of x is the denominator. So we have a hole when the numerator and the denominator have a common factor. Remember that first lesson of the unit that I was so excited about? It's my favorite lesson of the entire year. Remember that lesson when we had the top was factored and the bottom was factored and they canceled? When they cancel, we have a hole. Okay? So when you factor the top and you factor the bottom and you find something in common, you see a common factor that crosses out, you know immediately that you have a hole in that graph. A vertical asymptote, or the non-removable discontinuity, we've already said this, it looks like a vertical asymptote, right? The visual on that is a vertical asymptote. And that occurs when the denominator, or where the denominator, where the bottom, or what we call Q of x, equals 0. So if you ever see on the bottom, if you see P of x on top and Q of x on the bottom, if Q of x ever equals 0, that's where you've got a non-removable or a vertical asymptote. Now, we've got an even more detailed decision tree for whether or not there's a horizontal asymptote. So we ask ourselves, will you have a horizontal asymptote? Here's how to answer that question. Remember our friends P of x and Q of x? P was on top and Q was on the bottom. If the degree of P of x, or the top, the degree of the top is less than the degree of the bottom, or the degree of Q of x, then yes, you have a horizontal asymptote. And I'm going to write HA from now on. Yes, you have a horizontal asymptote, and it is at y equals 0. Okay, it's at the x-axis. Okay, so when the degree of the top, or the power of the highest variable on the top, is less than the degree of the bottom, then yes, you do have a horizontal asymptote, and it is at y equals 0. Now, if your degree of the top, P of x, is equal to the degree of the bottom, Q of x, then once again, yes, you have a horizontal asymptote, but this time it's not at y equals 0, it's at y equals the leading coefficient of the top, or of P of x, divided by the leading coefficient of Q of x, the bottom. And this will make much more sense when you see it as an example. But what we're saying here is, if you've got a degree of the top equal to the degree of the bottom, then you've got a horizontal asymptote. But this time it's not right sitting on the x-axis. If you take the leading coefficient of the top, divide it by the leading coefficient of the bottom, that's your y equals for your horizontal asymptote. Okay. Now, what if, and you can imagine what the third option is, what if the degree of the top, the degree of P of x, is greater than the degree of the bottom, the degree of Q of x? What happens then? Well, in that case, no horizontal asymptote. You do not have one. You may have a slant asymptote. If the degree of the top of P of x is 1 greater than, just 1 higher than Q of x, or the bottom, then you have a slant asymptote. Slant asymptote. And a slant asymptote is really just, instead of having a nice horizontal line, you have a line that might be on a slant, right? It might have a slope. Okay. So if the degree of the top is greater than the degree of the bottom, you do not have a horizontal asymptote, and you may have a slant if the degree is just one more than the bottom. And just to remind you on these x and y intercepts, because we do ask you to graph those and name those as well, just remember x-intercept is when you substitute 0 for y and solve, and an y-intercept is when you substitute 0 in for x and solve. Okay, so don't forget those as we're running through these examples. So let's see how a couple of these might play out. Let's take a look at number 1 here. Let's take a look here. Now, first and foremost, I want to check for holes, because again, that's my favorite thing in the world to do, is to factor and cancel and factor and cancel. So I want to check and see if I can factor and cancel. If I look at the top, I kind of see something that is a factor, right? And if I look at the bottom, I kind of see another thing that looks like a factor. X minus 4 can't be factored. X plus 2 can't be factored. So there won't be any factoring and canceling, so there won't be any holes. Darn, that's my favorite thing in the world to do, is to factor and cancel. But if you're not going to cancel anything, you don't have any holes. Let's check for my next type of discontinuity. Let's check for vertical asymptotes. Where did vertical asymptotes happen? That happens where the denominator equals 0. So for my vertical asymptote check, that happens when x plus 2 equals 0. So that must happen at x equal negative 2. Okay? So I must have a vertical asymptote at x equal negative 2. I'll draw that in here as best I can, and then I'll document that x equal negative 2. That's the vertical asymptote. Now, horizontal asymptote. Let's take a look. What is the decision tree for a horizontal asymptote? Well, I need to check the degree of the top and the degree of the bottom. So the degree of the top, if I look at this original here, the degree of the top is 1. So you have the highest power on any of these variables is 1. And the degree of the bottom is 1. So my degrees are equal. My degrees are equal. So the next thing I need to understand is, what are the leading coefficients of this? Because remember, when the horizontal asymptote is a yes, when these degrees are equal, that means my horizontal asymptote is the leading coefficient of the top divided by the leading coefficient of the bottom. What is the leading coefficient of the top here? The leading coefficient on this highest power variable is 1. And the leading coefficient of this bottom is 1. So the horizontal asymptote is found at y equal 1. So there's that. We also need to figure out what our x and y intercepts are, so let's go ahead and do the math on that. I like finding y-intercepts first, just because. So let's see, if I set x equal to 0, I've got 0 minus 4 over 0 plus 2, which is negative 4 over positive 2. So my y-intercept must be at 0, comma, negative 2. I'll go ahead and draw that in here. So I must have a graph that looks like this, right? My x-intercept is going to be found when I set y equal to 0. So my x-intercept is found when this equals 0, and I still have x minus 4 here, and x plus 2 here. Now, how do I solve this for x? A lot of people get confused by this. What am I supposed to do with this? There's a couple things you can do. You can think of this as a 0 over 1 and cross multiply. Or you can think of this as, well, in order to get rid of this bottom, I need to multiply x plus 2 on both sides. Either way is the same thing. If I was to cross multiply, 0 times x plus 2 is 0, and 1 times x minus 4 is x minus 4. So this cross multiplying gets me to x minus 4 equals 0, or x equals 4. So my x-intercept must be 4, comma, 0. 1, 2, 3, 4. And again, if you need to pause and replay that just to make sure that we understand how that works, go ahead and do so. But this thing lives like this, right? It does not cross that line, even though that might look like it did. It approaches it but never crosses it, okay? So all these values live along here. All these values live along here. And then you can use your calculator to help you even out this graph just in the interest of time. I'm just going to sketch this in here. So this graph lives something like this, but for purposes of domain and range, we've got what we need, right? The domain of this is everything, the green, everything, everything, everything until this little interruption here. So negative infinity all the way up to this negative 2x value. We take a break at negative 2, and then we pick back up on the other side and live for every other x value out there. And I'll go ahead and write that in interval notation. So it lives from negative infinity to that negative 2. It takes a break, and then from negative 2 to infinity it goes on. Range, bottom to top, it lives, 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 only takes a break at this horizontal asymptote here at a value of 1, and then picks back up again. So it lives everywhere except positive 1. So negative infinity to positive 1, and then on the other side 1 to infinity. So that's how that works. Let's take a look at number 2, because we have all different types of these things when they're presented to us. So this one looks different than this one. The top can't be factored. Let's take a look at the bottom. What can we do with the bottom? We can factor that. So let's make this look like this. 3x squared. This is a difference of squares, so let's factor that to be x plus 2 and x minus 2. Now, that doesn't help us with canceling, because I don't see any factors here that I can cross out, so I don't have any holes. Once again, don't get to do my canceling fun. But I do have things that are causing vertical asymptotes, right? And I actually have 2 things that are causing vertical asymptotes. I have each of these places that could be 0. So for vertical asymptotes, whenever x plus 2 equals 0, and whenever x minus 2 equals 0, I've got a vertical asymptote. So I've got one at x equal negative 2, and I've got one at x equal positive 2. So in this one, it's a very interesting looking graph. I have 2 vertical asymptotes, and I will not only draw both in, but I will also document both in the table below. Okay? So x equal 2 and x equal negative 2 are both vertical asymptotes that we will document here. Now, horizontal asymptote time, our little decision tree needs to be pulled out. We need to understand the degree of the top and the degree of the bottom. The degree of the top is 2. The degree of the bottom is 2. So remember what happened? That was the same thing over here, right? Degrees were the same. That means it's why we do in fact have a horizontal asymptote, and it is at the leading coefficient of the top, that's 3, divided by the leading coefficient of the bottom, that's 1. So we have a horizontal asymptote at y equal 3. So isn't this a funky looking graph? So y equals 3. Again, these are invisible lines that don't actually exist in the graph. They're just guiding lines. Now, let's investigate a little bit further. Let's figure out where our intercepts are. We have, let's see, I did intercepts in orange. So let's check out what our y-intercept is. If we set x equal to 0 in all of these cases, 3 times 0 on the top, over 0 plus 2 times 0 minus 2, we've got 0 over negative 4, or 0. So we have a y-intercept at 0, 0. Well, if that's the case, that means I must also have an x-intercept at 0, 0, right? It's the fun part about having something at the origin. So if you were to put this into your calculator, if you were to start doing a table of values and inputting various values for x and finding out the corresponding y's, you would see a graph that looks like this. It lives between these 2 lines like this, and it lives up here. And this by no means is exact, just because I'm showing you where it lives. But the graph looks like this. It's this orange part here. Okay? So there are a couple of breaks that happens for this domain and range. This graph, if you're coming in from the left and seeing where it lives from left to right, it lives, 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 takes a break at this horizontal asymptote, picks back up, lives, 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 takes a break at this vertical asymptote, and then picks back up again and lives, 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 lives. So there are 2 breaks in the domain. So we can list the domain. I'll do interval again just because I feel like it's the most difficult. So interval notation says the domain is from negative infinity to the break at negative 2. Then it goes from negative 2 to 2, and then it takes a break again, and then it lives again from 2 to infinity. So that's the domain. Now, the range is a little bit different. It also takes 2 breaks, but take a look at this. It lives on both sides. It takes a break at 0, but it doesn't pick right back up on the other side of this break. It actually takes a pretty big break and picks back up on the other side of this asymptote. Okay? So the range on this is actually from negative infinity to a y value of 0, and it's actually living right at that 0, so we're going to include that. And then it unifies on the other side of this big gap, and it lives again from a positive 3 to a positive infinity. Okay? So that's that one. Very, very interesting one. Let's keep the interesting train rolling here. Let's take a look at 2 more examples of different rational functions that you could see. So this rational function is one of my favorites. We take a look at this and we see the top and we say, wait a second, I can factor that, my favorite thing in the world. So let's factor this and see what we've got going on here. You can factor a difference of squares into x plus 2 and x minus 2. And the bottom can't really be factored, so we'll just write that x plus 2. Now, does everybody see the greatness that can happen? Yes, that's right. You can cancel the x plus 2. What does that mean we have? When we can factor and we have a common factor on top and bottom that cancels, what does that mean we have? Yes, it means we have a whole. And that whole is based on the fact that x plus 2, it's got a corresponding x value of negative 2. So if your factor is x plus 2, your x coordinate of your whole is negative 2. Okay? So your whole is at negative 2 comma what? How am I going to find the y value of that whole? I know the x value is negative 2, but we're not talking an asymptote that lives, right? We're talking about a whole that lives somewhere with an x value of negative 2. How am I going to find the corresponding y value? To find the corresponding y value, you plug in the negative 2 for the function, right? This is essentially y equals this, right? So to find the corresponding value, we put in, and you can put it into this remaining portion here, we enter negative 2 in for x. So that must mean y equals negative 4. So negative 2 comma negative 4 is the coordinate of our whole. Negative 2 comma negative 1, 2, 3, 4. That's where our whole lives. Okay? Now, since we've canceled this out, and we're just left with y equals x minus 2, we actually don't have anything in the denominator here. We basically have a 1, right? When we cancel this out, we have 1 over 1. We don't have anything but a 1 in the bottom here. So we don't have anything that could possibly cause a division by 0. So we don't have a vertical asymptote. Remember, the only thing that causes a vertical asymptote is something that would cause a 0 in the denominator. We don't have anything that could possibly cause that. There are no more variables left that could cause that. So now let's hit our horizontal asymptote discussion. Horizontal asymptote here, remember again we need to take a look at the degree of the top and the degree of the bottom. The degree of the top was a 2, the degree of the bottom was a 1. Let's go back to our decision tree. The top is greater than the bottom. The degree of the top is greater than the degree of the bottom. No horizontal asymptote. Okay, so we have none for horizontal asymptote. Now, how do we graph this thing? If you remember, if you cancel this out, you are left with y equals x minus 2. Y equals x minus 2. What does that look like? That looks like a line, right? That looks like a line with a slope of 1 and an intercept of negative 2. If you don't believe that, you can do a y-intercept calculation. You set x equal to 0, and sure enough, your y-intercept is 0 comma negative 2. What about x-intercept? Well, you can either count up with a slope of 1, you can go up 1 over 1, up 1 over 1, and say, hey, there's my x-intercept, or you can do the algebra and set y equal to 0 and solve for x. Sure enough, there we go, x equals 2. So we have an x-intercept of 2 comma 0. Again, this is a line, right? So this line goes like this through here. It goes here, so it lives like a regular old line with a slope of 1 and a x-intercept of -2. It just has a hole in it. See why this is a great one? Things cancel, simple lines are being drawn. It's an awesome problem. So our domain, we live from the left to the right. Live, take a break here. Where was the x-coordinate of this hole? It was at -2. I'll do set notation here, just for funsies. So the set notation here is x such that x does not equal -2. And the set notation for the range, bottom to top, I live, I take a break at a y value of -4. So y such that y does not equal -4 is my range on that. Okay? Alright, now let's put everything together and take a look at a problem that has vertical asymptotes and horizontal asymptotes and all kinds of everything all being brought together. So let's take a look here. Number 4. Can you factor the top and the bottom? Yes, you absolutely can factor both the top and the bottom. The bottom probably is most obvious to you. It's a difference of squares, x plus 3 and x minus 3. The top, what multiplies to 6 and adds to 5. Hopefully after you thought about that for a minute, you thought, well, it's probably 2 and 3, and they both have to be positive, right? So x plus 2 and x plus 3. Do we have factors that cancel? Yes, we absolutely do. We have the x plus 3 that cancels. So that must mean we have a hole. X plus 3 equal to 0. That means we have a hole at an x-coordinate of -3. So yes, we have a hole at -3 comma something. To find the corresponding y value of that hole, let's plug in the -3 into the remaining equation to find what y equals for the hole. This is the work for the hole. So we have -3 plus 2. I'm just putting in the -3 coordinate for the hole into here for x. So -3 plus 2, and then I'm going to put that same -3 here, -3 minus 3. So I have a -1 over -6. So, and we could call that a 1 over 6. So this hole is sitting at -3 comma positive 1/6. We're going to do our best to draw that here. -1, 2, 3 comma positive 1/6. That's pretty darn close to there. Okay? So that's where that's sitting, very, very close to the line. And that's our hole. Now we're looking at something that's basically, and let's call this y equals x plus 2 over x minus 3. Do we have a vertical asymptote? How do we know if we have a vertical asymptote? We take a look at the bottom and see if there's any way that that could ever be 0. Is there a way that that could ever be 0? This is our vertical asymptote work. Yeah, absolutely. If this is ever 0, we've got a vertical asymptote. That means the line x equals 3 is our vertical asymptote. Do my best to draw a straight line here. That wasn't terribly great, but there's our vertical asymptote. Alright, now let's take a look at our horizontal asymptote work. Our decision tree time. What's the situation with the degrees of the top and the bottom? The degree of the top was a 2. The degree of the bottom was a 2. They're equal degrees. So yes, we have a horizontal asymptote. And that horizontal asymptote lives at leading coefficient of top divided by leading coefficient of the bottom. Leading coefficient of the top is 1. Leading coefficient of the bottom is 1. So we must have a horizontal asymptote at y equal 1. Y equal 1. Let's take a look and see where our x and y intercepts are. Our y-intercept can be found, let me switch colors here. Our y-intercept can be found when x is 0. So let's see, our remaining equation here is x plus 2. So 0 plus 2 over 0 minus 3, which is basically -2 over 3. So I have a y-intercept of 0, comma, -2 thirds. Let's do our best here. 0 and -2 thirds, let's call it somewhere around there. Our x-intercept is found, let's do this work here. Our x-intercept is found when y is set equal to 0. So let's see, our remaining function here is x plus 2 over x minus 3. We can throw this guy over 1 and do a cross-multiplying thing. So 0 times this is 0, 1 times this is x plus 2. So 1 times x plus 2 equals 0, or x equals negative 2. So our x-intercept is negative 2, comma 0, negative 1, 2, comma 0. Well, I didn't draw that hole very well, did I? I should have made it look more like a hole. So let me sort of fix that a little bit here. Let me make that more into a hole. Sorry about that. So this graph lives through these intercepts that I just drew, and approaches there, and then it lives on the other side of this hole and approaches there. And we can do a table of values, but in the interest of time, this lives up here somewhere like that, right? So just for sake of the domain and range, we've got this graph sketched in here. We live, 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 take a break at the hole, live, 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 take a break at the vertical asymptote, and then live, 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 live. So our domain for this is, we'll do this in black, is negative infinity till the x-coordinate of the hole, negative 3. We pick back up on the other side of negative 3 till the vertical asymptote, positive 3. And then we pick back up on the other side of that, 3. On the other side of this vertical asymptote, this thing goes off to positive infinity for the x values. Ranged bottom to top, I live negative infinity all the way up to the y-coordinate of this hole. So negative infinity up to the y-coordinate of the hole. Unify on the other side of the hole, 1/6, all the way up to this horizontal y asymptote. I had a value of 1. And then on the other side of that horizontal asymptote, I pick back up and I go off to positive infinity. So 1 to positive infinity. Or you could have said y such that y does not equal 1/6 and does not equal 1, and x such that x does not equal negative 3 or positive 3. Okay, because you're picking back up on both sides of those discontinuities. Okay, so the key to these rational functions are these discontinuities. Where do we pick up our pencil? What kind of discontinuity do we have? Do we have holes or asymptotes? And we look at our algebra to help us determine where those live. The graphing calculator is not real great about helping us find these holes, and certainly not great about helping these graph these asymptotes. So drawing these in by hand is found most useful from the algebra here. Okay. So hopefully that got you a taste of how to do these. Definitely practice with the homework, the independent practice that you have, and let your teacher know if you have questions.